So I want to talk to you about arithmetic geometry of toric varieties, but I will give you a large motivation. I know some of you don't have maybe a strong arithmetic background, so let me first talk to you about the motivation, which is Arakelov geometry. So I will spend some time on this. If you have any questions, please just interrupt me and ask, and we will see where we end up with. So what is Arakelov geometry? So Arakelov geometry is an area of mathematics which lies in the crossroad between different mathematical fields, in particular number theory, algebraic geometry, complex analysis. And the starting point is the analogy between the spectrum of the ring of numbers of the ring of integers of a number field and an affine curve. And an affine curve C over any field. Over any field little k. Okay, let's see what this analogy is. Well, let's take as a leading example here, for example, the spec of the integer numbers whose close points are the prime numbers. And let's take C, just C. So let's start with the analogy. First of all, we can compactify C to a compact curve by adding only finitely many points. We can, on the other hand, compactify. This is actually not a compact space, but let's see what it means. So let's compactify this ring of integers, the spectrum of the ring of integers of a number field. So we can, the close points correspond to non-Archimedean absolute values. We can think of here as the p-adic absolute values, and we compactify them by joining the Archimedean absolute values. So this is like, let's see, the Archimedean absolute values. And then here the Archimedean. Or the Archimedean places coming from complex embeddings of the number field. So in the example we have, well, we can here take C union infinity and get P1. And versus we have here then the p-adic absolute values. And we adjoin the Archimedean absolute value. Okay, so of course, both spaces are different. So one is really a compact space. The other is just a patching of Archimedean and non-Archimedean places together. But the nice thing is that they share striking analogies. So let me just point out two. The first one is the product formula. So the product formula in the case of a complex of a curve means that if I take any rational function, then as we all know, if we consider meromorphic functions, then the number of poles counted with multiplicities is the same as the number of zeros counted with multiplicity. This is be a way to see the product formula there. So let's see so different from 0. So here the product formula says then if I count over all points, overall the order of P is 0. And on the other hand, if I take any element, non-zero element in my number field, or let's write here. Then if I take the product over all places, then the multiplication of the corresponding absolute values is equal to 1. Okay. In our example, if we take really the p-adic absolute values, so if you think of f taking the integer number and write it as a product of powers of primes, then the p-adic is p to the minus the exponent, and then you multiply it with a value at infinity, and it gives you 1. So this product formula is really the reason why maybe afterwards, if you want to generalize this to higher dimension, it's the reason why intersection theory works. And maybe I like to think of product formula, maybe for you with a background in tropical geometry, as being analogous to the balancing condition. So it allows for a well-defined intersection theory in the sense that if you have this product formula, or if you have a balancing condition, then no information will leak out at infinity, okay? Okay, and then the second striking analogy is the Riemann-Roch formula. So in the geometric setting, Riemann-Roch formula deals to compute dimensions of global sections of divisors. So in this case, we take a divisor on my compact curve and Riemann-Roch formula. Let me write it down in a maybe different way, as you all know. But Riemann-Roch formula can be written in terms of the Euler characteristic of the sheaf corresponding to your divisor D. And it says that the Euler characteristic of the sheaf corresponding to D, so this is an alternating sum of cohomology groups or dimensions. So this is equal to the degree of D plus the Euler characteristic of the structure sheaf. Okay, so if the degree is high enough, then this gives you the dimension of the space of global sections of D. Now, on the other hand, so Minkowski's theorems on the geometry of numbers, then you have also the analog in the number theoretic setting. So here you take a D in what is so-called a Rakelov divisor, or maybe a replete divisor, depends on the literature. So here you take one element like this. So you also look at this as a formal sum, finite sum, where index over all places. You allow integer coefficients where the places are non-Archimedean. You allow real coefficients where the places are Archimedean. So you have also an analog of the degree. Using really number theory, algebraic number theory, you have a notion of the Euler characteristic, which is the volume of some lattice associated to D. And then you have exactly the same formula. So the Euler characteristic of, now, let's say, of T is equal to this degree of D plus the Euler characteristic of O. That's right, the trivial sheaf OK. So this is also the volume of the this is this is exactly the same as the volume of the, I think this should be the volume of the, no, the square root of the discriminant of your number field. Yes. No, the volume. The volume. So the D gives the volume of a fundamental region of your lattice. It's always in the negative, yes. Yes. Here as well, you can compute the analogous of global sections, which in this world take into account the absolute value. So you talk about small sections, and these spaces are then are finite spaces with no algebraic structure, but still you have some ways of computing asymptotics of these numbers using this formula. Okay, so that's two things, and then I would say here that the goal of Arakelov geometry is really to extend this analogy to higher dimensions. Back to your question, it's minus log of the volume. So it can be negative, yes. Yes. It's minus log of the volume. Sure, yes. It's minus log. Okay, so you can extend this analogy to higher dimensions. Okay, so what does this mean? We want to generalize this to higher dimensional arithmetic varieties, and have then such that classical theorems in algebraic geometry have a number theoretic analog in this setting. So let's start with the objects that we want. So let X to respect of Z now be an projective flat scheme. So in the same way that we compactified our spectrum of the ring of integers of a number field, we want to compactify this whole thing by adding here the Archimedean places, and here then the corresponding complex fibers. Okay, so we want to compactify then the scheme by adding the Archimedean fibers. So these are so let me just draw a small picture. And then you see that then if you want to have analogous results, so you want this compound object to behave like if it were something projective over a field. Okay, so the picture is maybe you have something like this over spec of Z. You have here a P, and you want to adjoin here the infinite fiber, and here you have something complex. And this compound object, so putting both informations together, should behave like a projective thing over a field. Now, what objects does one consider? So here we had only the Archimedean absolute values. So the corresponding analog in higher dimensions were our metrics on, so here we have line bundles or vector bundles. Here we have metrics and Hermitian vector bundles and Hermitian line bundles with the Hermitian structure on the complex setting. So the objects are the objects that one considers now are the so-called arithmetic cycles, which are then, you talk about cycles like this. So this have then two parts. One is a cycle in algebraic geometry over the scheme. And then over the complex fiber, you want to have a so-called green function for Z. So I'm not saying exactly what this is, but this is then a green current. So this is a differential theoretic current on the complex space. Yes. We don't have a topology. It's really a compound object, so it's it's not a topological space. Yeah. Yes. No, this is not a scheme. No, it's really, this is a scheme together with some fibers at infinity. So, and this is then, is really said, is an algebraic cycle on the scheme, which is an algebraic geometric object. And this is then a green current on the complex space. It's really, and then you can define the so-called, you have intersection theory on the scheme, and you can define the so-called star product of currents. This gives you then a ring structure, and you can define your arithmetic chow group of X.
There's no compatibility required between the two pieces.
Yeah, sure. This is why that, I mean, the green current for set. Yeah, sure. Okay, but let's not spend a lot of time. So that my point here is also, so we have arithmetic cycles, and there is also a theory of characteristic classes for Hermitian vector bundles. So characteristic classes for Hermitian vector bundles. So these are then, it's also a vector bundle on your scheme together with a smooth Hermitian metric on the complex fiber.
Now, may I add something? The
Yes.
reason why people think about this simplification is because this arithmetic powering, which is also defined in a non-topological way, but the intersection product behaves as the intersection product and a complete variety.
Yeah.
And this is why you think about this as the complexification. If you just start with this already of the form X, it will not have these properties. Yeah. You will not have, if you have complementary codimension, you will not have finite intersection number and all these things that you would expect. And that's why I think there are a lot of people, I mean,
yeah,
you and I will think about this as a way of complexifying it. So making intersection as nice.
I think,
proper situation.
yeah. Thank you. Yeah, exactly. Yeah, so you think of maybe it's a definition of being compact in the sense that intersection theory can be well defined. Okay, so we have a theory of characteristic classes, so we can associate to such an element, so to such a Hermitian vector bundle, then an element in this arithmetic chart. And you have well-defined properties, so there are many applications. So I forgot to say all of this theory, also the extension to higher dimensions. So for surfaces, it was done by Arakelov, and then the extension was done by Gilles-Soulet in the 90s. And since then, a lot of applications have taken place. So let me write here. Of course, there is the whole theory of heights, which are then maybe the, so it's a way to say how arithmetically complex such an object is. So this is then the arithmetic analog of degrees. And most famously, well, this was then used by Faltings to prove Mordell conjecture. Also, lots of other equidistribution and Bogomolov type results, but I'm not going into anything of that. Just let me write down here some names. And the other is you have also an arithmetic Riemann-Roch in this setting, and this was by Gillet-Soulet, and was also used by Maillot and Rössler to link arithmetic, so to link heights with special values of L functions. So this is so important applications in this setting. But I want to tell you about some limitations as well. So some limitations of this theory developed by Gillet-Soulet. So there are maybe not only one, but the one I have been focusing in is that it deals only with smooth metrics. Okay, so it's only for smooth metrics. And as it turns out, if you look into maybe some natural metrics, they are not going to be smooth. So they don't apply to, and which is the first thing is the one I will start talking about today, is canonical metrics on toric varieties. These are not smooth. Okay. Another thing is if you are into the theory of modular forms or automorphic forms, then usually these are sections of some line bundles or of some vector bundles. There you have also some invariant metrics. And these invariant metrics, if you want to extend them to some compactification, then they are not going to be smooth anymore. They are going to have singularities, so the theory does not apply. So let's say automorphic vector bundles, like for example, the Hodge bundle of the moduli space of principally polarized abelian varieties that maybe you're familiar with. And there are also many examples related to the moduli space of genus G smooth curves. And it's the linear for compactification, where you have also metrics which are not smooth, hence the classical theory does not apply. So of course, a lot of work has been put into extending Arakelov theory to more singular metrics. And there has been results in that direction. So let me just name a few. No, the metric is on the bundle. Yeah. The metrics are on the bundle. So this is where this H. Yeah. So some results. So in the case of toric varieties, so for toric varieties, there is this book of, I'm just putting the indices. So Burgos, Philippon, and Sombra, who talk about arithmetic geometry of toric varieties, and they deal with these canonical metrics for line bundles. So they develop a theory for continuous metrics, continuous toric metrics on line bundles. This was then also generalized to more singular metrics on line bundles, also by Peralta and Gubla. So he does the Archimedean case, Gubla and Yulin Kai deal with the non-Archimedean case. There was a question? Yes. Yeah.
This vector bundle is sort of a vector bundle over each cycle and over the total space, or is it?
It's a vector. E is a vector bundle over spec of set, and you can take its complexification, and then it gives you a vector bundle over the complex fiber. And in that case, you can talk about Hermitian metrics on the complex fiber. So for toric varieties, there are this. There is also, yeah, maybe some log singular metrics on line bundles. Maybe I mentioned here also Burgos and Kramer and Kuhn. So maybe I put some years. This was 24. This was 2014. This was 2000 and also 2015. And then also 2024, there are some generalizations of this log singular metrics using some energies. My point is here, and also I want to mention here the theory of adelic line bundles. This was 2022, I think, or 20. I'm not sure. So they also deal with some singular metrics. But just point out that all of this is for line bundles. Okay. So really, no one has systematically studied singular metrics on vector bundles and to do the appropriate Arakelov theory for these vector bundles with singular metrics. So the best starting place, as it turns out with many different theories, is the case of toric varieties. Okay. So today I'm gonna focus on then say metrics on toric vector bundles. So today, and before starting to deal with singular metrics in a very general sense, well, we start with continuous toric metrics on toric vector bundles. So before passing to the toric vector bundles, I would like to tell you about the line bundles and to tell you what does it mean. So what one would like in the toric, for the toric so-called dictionary, is to have a combinatorial characterization of these arithmetic objects. So to extend the toric dictionary, you know, like projective polytope, global sections, integral points, Neffner's convexity, and so on, to the arithmetic setting. And this was exactly what was done in the line bundle case by Burgos, Philippon, and Sombra. So let me give you a review of the line bundle case. I have to say this is all now work in progress. And so nothing of this is on archive. So, so it's work in progress, and we're still trying to do some other things that from what I will talk to you today about. So maybe section 1 is then the line bundle case. And you will see also that for toric varieties, and the word tropicalization will pop up. So the nice thing about this case, it's so you saw in the general picture, we have always like the Archimedean and the non-Archimedean cases to consider. So we talked a bit about Arakelov theory. There is also a way to do adelic Arakelov theory, which is also using Berkovich spaces. You put metrics on the corresponding non-Archimedean spaces, and then you put complex metrics on the Archimedean space, on the Archimedean places. So we will take a bit a delic approach in this setting. And I will, so the nice thing about this theory is that it deals with both non-Archimedean and Archimedean places in exactly the same way. So the result is completely the same. So really you have a very homogeneous way of doing a Raketov theory. So here let K be either C or a discretely valued field. So we're going to do the local case. And over this field, then we consider a toric variety. Let X sigma be a complete toric variety over K with torus T. Okay, now we, this is the line bundle, so let's take a line bundle. So let L be a line bundle, toric line bundle. On X. And to this, we can associate the well-known piecewise linear function, which I will denote by psi. So the corresponding piecewise linear function. Okay, now we want to put a metric, and as anything in toric geometry that you want to have or that you're aiming for a combinatorial characterization, you have to put some invariance under the action of the torus. Now, for metrics, the torus is non-compact, so you cannot define a toric metric to be invariant under the action of the, so with an invariance property with respect to T, but you can do it with respect to the compact torus inside T. And this is then the definition. So a continuous metric, then let's say H. So maybe this is not exactly the definition of the metric, but let me think of this and write it down as on each fiber you have a norm, and you want this norm to vary continuously. So let me write it down in that way. So this is a norm on a one-dimensional complex vector space, on a one-dimensional, well, in the Archimedean case, you have a one-dimensional complex vector space. In the non-Archimedean space, you have also a one-dimensional vector space over a field, which is the completion of the function field corresponding to that point. But you can talk about norms on each of these vector spaces, and this is going to be the norm. Now, in one dimensions, these are all just positive real numbers. So here, X varies here. So we think of this metric as then collection of norms. And we say on L, so continuous with respect to also, of course, taking into account the line bundle L. And this is going to be toric if the following is true. If then the map, so let me write down here T to R. Let me write also here this with an H. So this takes then a point T, and here minus log of, so these are just positive real numbers. So I can take minus log of the corresponding norm. So this is log minus log of the corresponding norm. And I want this map to be invariant under, so here I have a map, evaluation map to NR. And this valuation map then takes a point T So let me write it down here. T maps under val. So N is the co-character lattice of T. It's a dual space of M, the character lattice of T. So it takes then an element in the dual M, and it maps it then to, I wrote it down here, so minus log of the absolute value of the corresponding character evaluated at T. Okay. So this is sometimes also called a tropicalization map. So we say that it is toric if this map is constant along the fibers of this valuation map or of this tropicalization map. Is invariant no, is constant along fibers of val. So note that this means then, so this you can also see NR as a quotient of the torus modulo the compact torus inside the T. So those with absolute value equal to 1. So let me just write it S. So this is what I mean. You're asking now for an invariance with respect to the compact torus. So this means now that we have a map from NR to R, which maybe I just write with the letter, what did I, phi H. Okay. So you have a map, you have a metric. The metric is toric if it induces then a map from NR to R. Now, given any map from NR to R, you can ask, when does this map extend? So this is given then by a metric on T. Okay, any map of this form, any commutative diagram of this form gives you a metric on T. So the question is, when does this extend to a metric on the toric variety? And then the answer will be, well, okay, if you have intuition, then maybe you want the local sections to extend. So you have a trivialization data. You want so the local sections will extend to the corresponding U sigma or to the corresponding affine toric variety. And this will mean that this function here is going to extend to the n sigma, so the affine tropical toric variety corresponding to sigma. Gluing the whole thing together gives you then an extension. So this will extend to a continuous metric on the whole toric variety if and only if this function then minus the one corresponding to the line bundle extends then to the tropical toric variety. So let me write that down. So we have to start thinking now about what is then for higher rank, how does this diagram look like? And yeah, what are the analogs? But let me write down the result for line bundles. So so this is a theorem which is proven in Burgos, Filipon, and Sombra. So it says that this H, so such a commutative diagram. So H extends to the whole line bundle. I'm just then to L if and only if this function pH minus the virtual support function or the piecewise linear function corresponding to the line bundle, if and only if this extends continuously to the tropical toric variety, which I denote like this. So it's a compactification of an R, which is the tropicalization of, oh, what's it called? Yes, so tropicalization of the toric variety. Okay. And the idea of the proof is exactly that. No, it's exactly, so you have the trivialization data of this, and then the corresponding sections will extend to the U sigma, and this means just that on n sigma you have that this minus the corresponding trivial data, so the corresponding character extends to this partial compactification, and then you glue everything together. Now there is also so this is moreover a correspondence. So the assignment in H goes to phi of H is a bijection between continuous toric metrics on L and continuous functions phi from NR to R such that the difference extends continuously to the tropical toric variety.
Continuity of these toric metrics, but in the Berkowitz space?
In the non-Archimedean case, yes.
Okay.
But this is true in both.
Okay, so in the non-Archimedean case, it's continuous on the Berkowitz space?
And in the, exactly.
Okay.
Yeah. Yeah. And the nice thing is that this is exactly, it's the same thing. Yeah. And then, so in particular, take your function to be equal to this. 0 extends continuously. And these are then the canonical metrics. The ones exactly induced by the function corresponding to your line bundle. Okay, these are the canonical metrics. And so let me just example. So in the we have then canonical metrics. Then you take phi equal to the piecewise linear function, and in the non-Archimedean setting, we have then the model metrics, and these are model metrics. These are then corresponding to models corresponding to a model. So this is going to be then you have a discretely valued field. You can take then the corresponding valuation ring, and then you have a toric scheme over this valuation ring, which is then, let me denote it by this curly X. And you want also a model of your metric. So this is going to be a toric scheme. This is then over spec of the valuation ring. And over spec of R, this is going to correspond to a piecewise affine function on some polyhedral complex, whose recession, so it's a polyhedral complex, but in the directions of infinity, you obtain your fan. Okay, so this piecewise affine function then is also, because of this asymptotic condition, is going to satisfy this. So this gives you also the a model metric or a continuous metric in the non-Archimedean case. Okay, now let me go to,
Okay.
yes.
You're not saying canonical metric is a model.
No.
Different examples.
I mean, yeah, no, a canonical metric is a special example because there are canonical models which just give you by the polyhedral complex, which is exactly the same fan. And there, if you take that one, the canonical model, then this gives you exactly the canonical metric in the non-Archimedean case. Okay, and there are really, in that situation, I maybe just say it orally, but you have also nice positivity results which relate concavity of this function. So this is, the metric is semi-positive, and there is a notion of positivity of metrics, and then the metric is going to be semi-positive if and only if this function is going to be convex. So in particular, by taking a dual, it defines a continuous function on a polytope. And at the end, well, the main result of the book I mentioned is the computation of the height of the toric variety, which at the end is going to be just an integral over these polytope with respect to the function on the polytope, which is the dual of this one here. Okay. But if you're interested more in that, we can talk later, or I can give you also references. So let's talk a bit about the vector bundles. So we need an analog. And the analog of, maybe if we think of this as the space of norms, we need an analog of course, of this. We need an analog of this. Okay. So let me talk first of in the Archimedean case where we have a result. So in the Archimedean case. So let's say for k equal to c. So in this case, we use the theory of to do the analog of the corresponding. So we have a toric vector bundle. So the analog of this one, we use the characterization of Kumar Kave and Christopher Manon and Boris Chelikovsky. Maybe I want to leave this. No. No, that's also the tropical.
Minus log absolute value is still a Archimedean one.
Archimedean, no.
Minus log absolute value in the Archimedean world, yeah. That's all the complex one.
Mm-hmm. But
So it is the amoeba map. But you don't see an amoeba because it's the whole space.
maybe I leave this. Okay, so this is also very explicit. So we are in the Archimedean case. Now let E be a rank R toric vector bundle. So it's very good that these were also considered yesterday. So it's a toric, so it's a vector bundle with also an equivariant structure. So a toric vector bundle over my toric variety. And then, so the result of Kumar, of Kave and Manon and Chelikovsky is that this toric vector bundle, also this this data that so this Kliashko data, which was then yesterday like considered in matroidal terms, they considered it as a map, as a piecewise affine map to a cone over the spherical building. So so this corresponds to E is in correspondence to a piecewise linear map from, in this case, NR to, I'm gonna write it down as they do. So let me here, this is maybe a cone over a spherical building over GLRC. So let me just write down maybe what this is. So as a set, you can think of this as the set of so-called pre-valuations. So these are maps E from your, let me fix here a vector space. So V is just going to be the fiber over a distinguished point of the toric variety. So this is just E to the R. So these are maps from V to R, adjoint infinity. And you want to satisfy them to satisfy like the analog of valuations. So you want to E of lambda V. But you think of this as valuations, but with a trivial absolute value. So here you want this to be E of V for lambda in your C. And you want E of V1 plus V2 to be bigger or equal than a minimum. And of course, E of V is infinity if and only if V is. So this space of, they call pre-valuations, comes also with a simplicial structure. And you can talk about piecewise linear maps. So this is, so you can also, this has the simplicial structure of a building. So this has like distinguished apartments, which are going to be in this case then linear spaces. So it's a cone over a sphere. So you can talk about being piecewise linear here. Okay, piecewise linear with respect to the fan. So this means that over each cone, the map between the corresponding cone and the corresponding, so it lands in an apartment, and the restriction then is going to be a linear function. And let me just write down the functions explicitly, because if there's a really, so that you have a feeling from, it's a, so what is this map? So the important thing about all classifications of toric vector bundles are the local triviality of the toric vector bundles with respect to the affine toric varieties. So over each cone, the vector bundle is trivial, and trivial with an equivariant action. So it's equivariantly trivial. So this means that over each cone, so over each cone, we have the local, so E restricted to the corresponding toric variety is trivial. Then we have trivialization data. These are, so we have an equivariant action, which are then given by some characters. And we have a frame. This is a frame for E. Okay, so these local pieces are actually giving you the whole information about your toric vector bundle. So and if you have this for a cone, then for X in R, so in a cone, then really you have this map of E. Then as a pre-valuation, so you X you evaluate it in an element of V, this is nothing more than the minimum of the X with the trivialization data for EI different to 0, where you express E as a sum with respect to the frame. Okay, so so this function is really explicit. You just need the trivialization data. So using this, we now have at least the analog. We have now the analog of this. Okay, so what is the space of norms? So it's the space of Hermitian inner products. It's the symmetric space. So instead of R, we're going to take the space of Hermitian inner products on V, on a complex vector space of dimension R. And let me just write down the diagram and state the result. So now we have, so I have to say, now we want to define what a toric metric means. So a metric, now the same. H is then, you see then on each fiber, we want such a Hermitian inner product is toric. If now you have a map then from T to S, so this is symmetric space. So GRC modulo the unitary matrices. So let me write them U. Okay. If and only if this map, which just takes then a T to the corresponding Hermitian inner product on the fiber, if this is again invariant or constant along the fibers of your valuation map. So again, we have a evaluation map here to NR, and we have now then this toric condition gives you then a map to S. Now we now have a map to S. So what does it mean to extend continuously? So this will then what we have is the following. And you see that the analogy is there. So now to state exactly the result, we have to do a bit more work. So let now alpha E. So the thing is we have now two maps with target S. I want to express some kind of continuity for maps, a map going to the spherical building to the space of pre-valuations and this map over here. So you can compare both because both gives you, so this is Hermitian products on V on a complex vector space. The other one is pre-valuations, which also take elements, so are functions on the complex vector space. So what we need is to be able to compare both is to to use the maps. So this is as follows. So let this map then go from V to space of PL functions and R to R. So this is like another incarnation of your vector bundle. So this goes from V to the map, which takes X to your map, your piecewise linear map X. So it's just evaluation on your E. And then on the other hand, then we have FH from V to continuous and R to R, which goes then E gets sent to X, goes to a minus log. And this then, this Hermitian inner product evaluated at EE, maybe I call it V. And Z, so it's val of Z equals to X. Okay, so now we have a way to compare both things. And now the claim, so maybe I write it as the theorem over here. And this is joined with the authors that I mentioned, is that H, so in the same way, you can also just consider commutative diagrams in this case, which just means toric metrics on your torus. And you can ask, when does it extend to a continuous metric on the whole toric variety? And the result is that is similar to the line bundle case. So this extends to the whole toric vector bundle if and only if this difference extends to a continuous function on the tropical toric variety. So if and only if f h minus L E extends to a function, to continuous functions on n sigma comma on. And this is moreover also a bijection. So to each function which satisfies this, to each function like this, which satisfies this asymptotic condition, you have an associated toric continuous metric. So in particular, also in this vector bundle situation, you have these continuous, these canonical metrics. So there are some things in the non-Archimedean case, but let me make